Welcome back to G Fun Facts Online. Today we are going to talk about a revolution that is happening on a scale so small, it is almost impossible to see with the naked eye. Yet it promises to change the fundamental way we think about computing, medicine, and the internet itself. We are moving away from the massive, energy-hungry server farms and silicon chips we are used to, and diving into the world of photonics. Specifically, we are going to explore a technology called the diffractive tip. Imagine taking the colossal power of an artificial intelligence, a deep neural network that usually requires heavy graphics cards and electricity, and shrinking it down into a footprint smaller than a grain of sand. And here's the kicker. It requires absolutely no electricity to perform its calculations. It thinks using only light. This isn't science fiction. It is a technology that is being built right now, with major breakthroughs occurring in 2024 and 2025. Today, we are going to break down exactly how you can turn a strand of optical fiber into a supercomputer, how we physically print a brain onto the end of a glass hair, and what this means for the future of our world. To understand why this is such a big deal, we first need to look at the current state of our infrastructure. For decades, the optical fiber has been the unsung hero of the information age. It is the backbone of the internet. These thin strands of glass carry the world's data from continent to continent as pulses of light. But historically, the optical fiber has been a dumb pipe. It is a passive tunnel. It carries information, but it doesn't understand it. In our current system, data travels as light. But to do anything with that data, to read it, route it, or analyze it, we have to convert it. We take the light, turn it into electricity, feed it into a silicon processor, crunch the numbers with billions of transistors, and then, often, convert it back into light to send it on its way. This process is called optical conversion, or OEO. It is the great bottleneck of modern computing. It generates massive amounts of heat, consumes vast amounts of power, and, perhaps most critically, it introduces latency. It takes time to switch from light to electricity and back again. But researchers asked a radical question. What if the pipe could think? What if we didn't need to convert the light to electricity at all? This is where the concept of the diffractive tip comes in. The idea is to transform the transport medium itself into the computer. By fabricating complex, nano-scale structures directly onto the tip of a fiber, engineers have created a physical structure that acts as a deep neural network. When light exits the fiber and passes through these microscopic printed layers, it diffracts, it bends and interferes with itself. And this is the magic trick. That interference pattern isn't random. It is a calculated mathematical operation. Just as a digital neural network multiplies inputs by weights to get an output, a diffractive optical neural network uses the laws of physics to compute the answer. By the time the light hits a detector, the processing is already done. The pattern of the light is the answer. This is inference at the speed of light, with zero electrical power consumed for the calculation itself. Now let's get into the physics, because this is where it gets fascinating. How can a piece of static plastic or glass perform complex logic? We have to look at the nature of light and the Huygens-Fresnel principle. In a standard computer, a neural network is made of layers of neurons, which are just mathematical functions. In a diffractive deep neural network, or D2NN, those neurons become physical reality. Imagine a tiny, transparent screen placed at the very tip of the fiber. This screen isn't flat. It has a rugged terrain of microscopic hills and valleys. When a wave of light hits this terrain, the physics of the material comes into play. The hills, which are thicker parts of the material, delay the light's phase. They slow it down slightly relative to the light passing through the valleys, or the thinner parts. Every single point on this microscopic screen acts as a secondary source of a wave. As the light radiates from these points, it interacts with light from every other point. Where the peaks of the waves meet, they amplify each other. This is constructive interference. Where a peak meets a trough, they cancel each other out. Destructive interference. By carefully designing the height of every single point on that screen, engineers can control exactly how the light interferes. If you design the structure correctly, you can make it so that if the input light represents, say, an image of the number 3, the diffraction pattern will focus all that light onto a specific spot on a detector that corresponds to 3. You have essentially built a lens that doesn't just focus light, it recognizes patterns. But one layer usually isn't enough for complex thinking. Deep learning requires depth. So in the diffractive tip, multiple layers are stacked on top of each other, separated by tens of microscopic wavelengths. Light passes through layer 1, diffracts, travels through a tiny space, hits layer 2, diffracts again, and so on. This cascade allows the system to approximate extremely complex, nonlinear functions. The weights of the neural network are physically frozen into the thickness of the material. To train this brain, you don't run electricity through it. You use a digital computer to simulate the diffraction, adjust the height map of the layers virtually until the system gets the right answer. And then, once the design is perfect, you print it into reality. Speaking of reality, the fabrication of these devices is a marvel of modern engineering. We are talking about building a structure with the complexity of a skyscraper, but on the head of a pin, where every floor must be aligned to within a few nanometers. The technology that makes this possible is called two-photon polymerization, or TPP. Standard 3D printers use UV light to cure resin, but they are too clumsy for this scale. TPP uses a femtosecond laser. This laser pulses for 1/4 of a second. The resin used is transparent to the laser's wavelength, so the beam passes right through it without doing anything, except at the very focal point. At that exact microscopic point, the photon density is so high that the resin molecules absorb 2 photons at once, triggering a rare quantum event that cures the plastic instantly. By moving this laser focus in 3D space, engineers can write the diffractive structure directly onto the flat, cleaved end of an optical fiber. It is like using a laser pen to draw a 3D sculpture inside a drop of liquid glass. This method, often called the dip-in method, allows for the creation of structures that are perfectly aligned with the fiber's core. This brings us to the major breakthroughs of 2024 and 2025. Researchers, including groups at Tsinghua University, moved beyond just printing on chips. They developed the fiber D2NN, where the logic is integrated inside and onto the fiber itself. They utilize something called mode coupling. A multimode optical fiber supports many paths or modes that light can take. By introducing controlled mechanical changes or specific index of refraction changes inside the fiber, researchers can force the light to mix and couple between these modes to perform computation. The fiber effectively becomes a 1D processing unit, with the printed tip acting as the readout layer. The transmission line has become the processor. So why do we need this? Why go through the trouble of printing microscopic brains on fibers? The answer lies in 3 key factors: zero latency, zero power, and an ultra-compact form factor. Let's look at the killer applications. The most immediate life-saving application is in medicine, specifically the intelligent endoscope. Imagine a doctor performing an endoscopy to check for colorectal cancer. Currently, they navigate a camera, find a suspicious polyp, cut a piece off, and send it to a lab. The patient waits days for a result. With a diffractive tip neural network, the endoscope doesn't just see the tissue. It knows what it is looking at. Light illuminates the tissue, and the scattered reflection enters the fiber tip. As that light passes through the diffractive layers, it is processed instantly. If the tissue is healthy, the light diffuses to one side of a detector. If it is cancerous, it diffracts to the other. The doctor sees a malignant or benign overlay on their screen in real time. Research in 2025 has already demonstrated these networks classifying tissue textures and specific cancer markers with accuracy rivaling standard electronic computers, but without the bulky hardware. Another massive application is in telecommunications. Our global internet relies on signals traveling thousands of kilometers. These signals get distorted by noise and non-linear effects. Typically, we use power-hungry digital signal processing chips to clean this up. The fiber D2NN offers a passive solution. A diffractive segment at the receiver can be trained to simply undo the distortion. It acts as an all-optical equalizer. In 2025, researchers demonstrated a fiber neural network that identified modulation formats with 100% accuracy in noise-free conditions, entirely optically. This could slash the energy footprint of data centers and undersea cables, which is a massive win for green technology. There are also applications in robotics, specifically minimally invasive surgery. Knowing the exact shape of a catheter inside a body is critical. By training a diffractive tip to recognize the speckle pattern, the messy interference of light caused by the fiber bending, the fiber can feel its own shape. It becomes a proprioceptive nerve for the robot, reporting its position with micrometer precision, immune to magnetic interference. Of course, no technology is without its challenges. The diffractive tip is not magic, it is physics. One major hurdle is the wavelength problem. These networks are typically trained for a specific color of light. If the laser shifts due to temperature changes, the diffraction pattern shifts, and the calculation fails. Researchers are currently working on broadband D2NNs that work across a range of colors, but this requires even deeper networks. Another limitation is that it is a fixed brain. Once you print it, it is read-only memory. You can't update it like software. The future vision here is the programmable diffractive tip, using phase-change materials that can alter their refractive index with heat or electricity, allowing us to flash new algorithms onto the fiber tip in the field. And finally, there is thermal expansion. If the polymer expands by even 1% due to heat, the brain stretches and the logic breaks down. Materials science is racing to create zero thermal expansion photopolymers to solve this. In conclusion, the diffractive tip represents a shift from the age of electronics to the age of smart matter. We are no longer just shaping materials to be strong or transparent. We are shaping them to be intelligent. We are distributing intelligence to the very edge of the network, giving eyes to surgical tools and brains to internet cables. As we look toward the future, the definition of a computer is blurring. It isn't just a box on a desk anymore. It is a transparent coating, a microscopic lens, a fiber tip. I want to leave you with a scenario from the year 2035 to illustrate where this is going. Imagine a search and rescue robot snaking a thin optical tendril into the rubble of a collapsed building. The fiber tip is no larger than a grain of salt. It emits a pulse of infrared light. The reflection returns, passing through 50 layers of nano-printed polymer on that tip. There is no cloud connection. There is no heavy processor. The computation happens in the flight of the photons themselves. In less than a nanosecond, the diffractive tip processes the spectral signature of the air and sends a signal back up the fiber. Human breath detected, 99.8% confidence. The robot stops. The dig begins. That is the power of light-speed thought. Thanks for listening to G Fun Facts Online.